Good morning from my side. It's great to be back. It's also the third time for me, I think, so we have a similar track record on this, Alex and me. So my lectures will be, is it a bit too loud? My lectures will be on topology. There will be symmetries as well. And let me quickly give you a plan of what I'm going to do over these 3 lectures that I have, 1 today and 2 tomorrow. So today, we are going to start to learn about topology in 1D. So I'll basically exactly start where Alex left off and define a simple 1D system which actually has chiral symmetry and walk you through the different ways of looking at it and where topology plays a role. Then, so this is basically going to be the SSH, the Higa model. Then we are going to talk about 2D churn insulators. And then that's, I think I'm maybe not even finishing this today. And tomorrow we'll talk about, the main subject will be spatial symmetries and topologies that are protected by these. And that goes under the name topological crystalline insulators. And in particular, I'll highlight a subclass of these, which are going under the name of higher order topological insulators. Okay, so that's the plan, just so that you know what's coming up. Before I jump into the first subject, just as Alex did, I'd like to give you a quick sort of overview or survey of what I think is important to understand when talking about topology. So what are the fundamental principles, or what is it that we call topological in many body systems in condensed matter? So first of all the things, at least that's the spirit in which I'm going to talk about topology. All the things topological should have some notion of universality to them and some notion of robustness. So when we change the system a little bit, this topological property that we are after shouldn't change immediately. And so the question is, what are the concepts that are crucial to provide us with such notion? And there are 2. So basically, okay, for you it was 3. It was symmetries, dimensionality, and topology. Okay, yeah. So I have 2 things to offer. So so what we are doing is really we are classifying systems of matter, right? Systems with many degrees of freedom. And so previously they were classified by symmetry breaking paradigms, like a magnet, for instance. A ferromagnet would be one class, and every ferromagnet would belong to the same class. And if we want to do a topological classification, again we need an equivalence relation. We have to say when do we consider 2 systems being equivalent, and the equivalence relation that is most prominently used, I guess, is the adiabatic principle. And that is convenient, of course, to use when there is a gap in the system. So that, I think, for those of you who were in the preschool, Barry, I think, was talking about adiabaticity a lot. But of course, this is not the only way to define equivalence principle. You can also, for instance, if you don't want the spectral gap, but more work in disorder systems, which is what Alex used to do, or is doing, then you would maybe more worry about a mobility gap. But in any case, you want some way of deforming your system and saying, these are the deformations allowed. And the other concept that's crucial is locality. So if we have no notion of locality, we, for instance, cannot define dimensionality, right? So if we want to define on the most general, setting topology for a quantum system, we need to know which degrees of freedom can be coupled with local interactions. That's the rule of the game, and which can't. Okay, so that's just that comment. And now, the setting that we are going to consider in order to make use of this fact that we have a spectral gap are all 0 temperature ground states of local Hamiltonians. So that is really the setup for these lectures. People have extended the concept of topology to many other settings, excited states, and so forth, but it's not the focus here. Just for you to know that you don't get confused when you look at more recent papers. But this is what we mean. And now there is still a big, another big sort of distinction of what can be meant by topology in condensed matter. And that concerns so-called short-range entangled phases. And long-range entangled phases. So that is a distinction that these words came already up in Alex's lecture. So phases that are long-range entangled are also called topologically ordered or intrinsically topologically ordered. And their characteristic feature is that they have a ground state degeneracy that is non-trivial and depends on the genus or the topology of the manifold on which the system is put on. Ground state, more generally, it really depends on the system size, yeah, and its topology. Ground state degeneracy depends on manifold, on the spatial manifold on which the system is defined. And the second important thing is that these ground states cannot be distinguished. These degenerate ground states cannot be distinguished by local measurements or local observables. So this is a really minimal definition and embraces everything that I think goes under the name of topological order. And you see it really requires these two concepts. So I need my gap. I need to talk about ground states somehow, which are separated from excited states. Or maybe I should also mention that, of course, the ability to take a thermodynamic limit is important, right? Topology is really only defined for thermodynamically large systems in a strict sense. And then the other thing is locality, right? Otherwise, the second property cannot be formulated. So a ferromagnet, to contrast, can be measured and make the ground states can be distinguished by a local observable. Okay, so why am I telling you this? And so what goes into this category, the most prominent case, for instance, is the fractional quantum Hall effect. The toric code, if you have heard about these words. And more recently, there are these fracton phases in 3D. So these are more theoretical concepts. I'm just dropping names here for those who have heard them to just put their thoughts in the right category. If you haven't heard them, also fine. This stuff is what we are not going to talk about in this school. Yeah, this is not our interest. Our interest is on that side of the board. And here we are talking about quantum systems which do not have this sort of exotic ground state degeneracy property, but here, and I don't repeat what Alex has already said, here we can think of either more interacting or less interacting systems. We can ask, are these made of fermions or not, and then we can go with all these classifications. And what we will be mostly focused in my lecture is states that are based on a band structure classification or band structure point of view. But that's, of course, a limitation that we use here for convenience is not fundamental in any case to understand topology in short-range entangled phases. Okay, good. So that was maybe a few preliminary or starting remarks. Now let's go right into the. By the way, questions, as said before, are very much encouraged. So please stop me anytime. Okay, so we are going to start with the most, let's say, really archetypal model of topology in band structures, and that goes under the name Higa model. It's closely related to the Rice-Millie model that you've heard about in Barry's lecture, I believe, or somebody must have talked about it in the pre-course. So this is really like the, I don't know, the hydrogen atom of condensed matter topology. And if you understand this one well, I think you already got quite far, or you can build up and get understanding of many other systems as well. So, so the system was originally meant for an organic molecule called polyacetylene. And that molecule has sort of this zigzag structure and alternating bonds that are stronger and weaker. So what we are looking at here is just a chain where the degrees of freedom that we put is a spinless electron or a spinless fermion on each side. So we forget about the spin degree of freedom, and each side of this chain can be occupied with an electron or empty. And now there are the only ingredient in the Hamiltonian are hopping integrals between nearest neighbor sides. And these hopping integrals, they vary in strength. They are t times 1 minus delta between the sides, the first side and the second side. And then it's t times 1 plus delta. And then again t 1 minus delta, and so forth. And now you see that this doubles the unit cell compared to the one that you would have guessed when I just draw the atoms. So two sides are in one unit cell, and we call them A and B sides to distinguish. So in the unit cell, there's 2 degrees of freedom. Okay, and the Hamiltonian, if you wish to write that down in second quantized notation, suppose we have a system of L unit cells, then the first hopping is within the unit cell, C dagger AI, C BI. And then we hop with 1 plus delta out of the unit cell, C dagger BI, C AI plus 1. And the Hermitian conjugate, right? Okay. So, so it's most convenient to look at this system with periodic boundary conditions, where we can then go to momentum space and look at the Bloch Hamiltonian instead of this beast. So if we have that, then we can, again in second quantization, talk about a momentum in the Brillouin zone, and we sum over the sublattices. Let's say we have 2 indices alpha beta which run over A or B, and then we can take write the Hamiltonian as a form of a Bloch matrix, C dagger alpha k H alpha beta. That depends on k, so this is now a 2 by 2 matrix, C beta of k. And that 2 by 2 matrix, H of k, takes the form. Well, what form does it take? So there's no hopping between A and A or any interaction between A and A, right? So the upper left entry of this matrix should be 0, and same between B and B. And now when I think about what happens between A and B, there's this term in the unit cell, which will give me, okay, the T, I pulled it out.
Can you
Sure. Like that? Is that okay? Or I move myself up. I can I'm just afraid that I would fall off the stage.
No, that's fine.
Okay? Yeah, no, that's fine, but I might not. Okay. Is this also fixed? I'm just going to be forceful. Okay, good. Okay, so on-side hopping was 1 minus delta, and then 1 plus delta times e to the ik to hop out of that unit cell, and then the whole thing should be Hermitian. So it's 1 plus delta is e to the minus ik. Okay, cool. So that's that Hamiltonian. Actually, we can rewrite it yet in another way by expanding it in Pauli matrices, since it's a 2 by 2 Hamiltonian. So it's nice to write a Hamiltonian of that form as sigma x times some function of k, which is given here, plus sigma y times another function of k that would be given by 1 minus delta, 1 plus delta sine k. And then in principle, there would be a sigma z and a sigma 0 term, but well, obviously they're 0 in this particular example. Okay, so so what we've done is basically we've put this Hamiltonian in the form h of k, this Hamiltonian matrix, is some vector d of k dot sigma. Yeah. Okay, and now we want to talk about topology. So what are the sort of the universal properties of this Hamiltonian, which are not depending on the details that I choose? And so first of all, the question is only well defined if we have a gap. So the spectrum of such a Hamiltonian is easily determined by squaring it. So the spectrum is consisting of 2 bands, obviously, because it's a 2 by 2 matrix. And I'll call them epsilon plus minus of k. And they're just given by plus minus the magnitude of this vector d. Yeah? So we see that we have a gap everywhere in the Brillouin zone as long as this vector d is not 0 at any point. Yeah? So to have a gap system, we want to impose that d of k is not equal to 0. Okay? But what else can we now say about how to classify these types of Hamiltonians? Well, what we can do now, luckily, this d that we have is only 2 components, so we could maybe draw these 2 components and see what they do as we go through the Brillouin zone. So let's say this is an axis dy and dx. So let's forget about dz for the time being. So what we see is that condition excludes from this 2-dimensional space the origin. Yeah? This is excluded. So this is now a punctured plane, if you wish. And now we can look at the trajectory of the point that's described by this d vector as we vary k in the Brillouin zone. And in this parametrization with this delta here, I'm claiming that there are 2 distinct trajectories, yeah, which are not smoothly transformable into one another. Which are these?
Enclosing the puncture hole or not.
Okay, perfect, exactly. So either I can do this, yeah, or I can do this. Okay, and this is, I guess, for delta larger than 0, and the other one is for delta less than 0. And you see that by changing delta, there's really discontinuity between these 2 situations, because I'm not allowed to pull that line over the origin, because then I'm losing the gap, right? Okay, so there is this topological distinction. Of course, I could have also defined a Hamiltonian that does multiple times go around the origin. That's what we'll see later is a winding number or an integer classification, but already with this Hamiltonian, we have these two different realizations. And so this is exactly the kind of thing that we talk about when we say we have a topological distinction. Now, to get to this point, what was important to do is okay, I'll keep my Hamiltonian here. It was important to remove that sigma z, right? Why is that important? If there was in the Hamiltonian a term, dz times sigma z, I would have a third axis on this space. It would still be a puncture space with the origin excluded, but then any path that I have here could just be deformed into any other one by going in that third direction, right? It's like, you think of a rubber ring or something, and you have that point here in the middle, but you could, deform anything to anything else if I could go in the third dimension. So it seems important to exclude that sigma z appears in the Hamiltonian. So dz of k from Hamiltonian. Okay, and this is where symmetry restrictions will come in. So what we understand, if we would write the most general 1D Hamiltonian, that thing, it would say as a 2x2 matrix, this kind of topological distinction wouldn't work. Yeah? And so to make it work, we have to somehow get to this result that we exclude one of the Pauli matrices. And there are two ways to do this, which we'll discuss separately. The first one, so there's two ways. The first one is, and that nicely blends in with Alex's lecture, that we impose on this Hamiltonian a chiral symmetry. And so that is like this S-type symmetry. And in this case, the chiral symmetry, what would it be? I want to exclude, let's see whether you remember how it acts. So what would the chiral symmetry be? It's this S symmetry, right? So it's like S of H of K times S inverse is minus H of K, right? Okay, I think Alex didn't have a K, but let's assume that we have a K now. It doesn't really matter. So what is my S? What can I use for S to get to this result? Sigma z itself, right? Okay. And what does that physically mean? It physically basically means that there is no coupling, so that all the couplings are off diagonal, right? When I always couple A and B sides, even with longer range hoppings or anything, then I would always have just sigma x and sigma y contributions. I would never have a diagonal element in my Hamiltonian. Okay, so that's great. So our Hamiltonian has that symmetry. That's option number one. And this is obviously a local kind of symmetry. So I've just, this transformation here on the Hamiltonian acts just on the local degrees of freedom. Yes?
So we have this chiral symmetry because we only have couplings that connect the two sublattices. So does this hold for more complex models where we have like 3 or 4 orbitals per side?
So you could construct a chiral symmetry, or you could have a chiral symmetry, but it's not a generic thing to have. So if you think about like just a solid, which had hoppings derived from whatever, take a DFT calculation, get your hoppings, you'd never have a chiral symmetry, right? It would be a huge coincidence. However, I should say that often such a chiral symmetry emerges effectively at low energies. So for instance, in the example of graphene that Alex talked about, at low energies, it's a Dirac equation, and it happens to have such a chiral symmetry. But then you have to really think about like what energy scales are you talking about, and you can sort of use this chiral symmetry if you want to derive something about the low energy physics. But globally, like the world that we live in doesn't have chiral symmetry, so neither has that Europe.
Maybe if you're just making a time-binding model to first neighbors.
Yeah. So then it might be a good approximation either in that sense or at low energies. That's typically what happens. Yeah. And then you have to ask, like, once you discover something interesting that's protected by the symmetry, then you have to ask, well, how good was your approximation? By how much is it broken in the real system? And then you can gauge, how useful your result is, let's say, for a real system. Yeah. That's how I say it. Yeah. So it's a useful thing to consider, but of course you have to also ask yourself how realistic is it in the end. But there is now another version of imposing this. This sigma z equal to 0, or dz equal to 0. And that is completely sort of physical, I think. It makes use of time reversal symmetry and inversion symmetry. So time reversal symmetry, here, because we have spinless fermions, it's just complex conjugation, yeah? Complex conjugation. And inversion symmetry, what does that do? So what I mean is the inversion symmetry with respect to a bond, mid-bond, yeah? Like at this point. That's the only one that I could define because I have already this alternation between weak and strong bonds. So the sides A and B are certainly not inversion centers, right? So what does that thing do? Well, if you reflect this chain about this point, you certainly, for one, you move space x to minus x, but also you exchange in the unit cell the sublattices A and B, right? And that exchange is mediated by sigma x. Sigma x is changing A to B and B to A. So the inversion symmetry action is sigma x times h of k times sigma x is h of minus k. Yeah? Minus because I'm inverting the spatial direction. Okay. And so what are the restrictions of these combined symmetries on our system? For one, it would say that, so dy, I should also say time reversal, of course. It says k times h of k times k is also h star of, sorry, not h star, that's why we have the k for h of minus k, right? So, so time reversal also changes momentum to minus the momentum. So this imposes that dx is even in k, dy is odd in k, and dz is equal to 0 because the first thing would say it's even in k, and the second thing would say it's odd in k, and that's not compatible. So that's another way to get to dz equals 0. We see that these combination of symmetry actually impose an even stronger constraint than the first one on our Hamiltonian. It says this needs to be an even function, this needs to be an odd function. That's satisfied by this Hamiltonian, but of course it's stronger than what the chiral symmetry requires. Okay, so in both cases we'd have this topological difference, but these two cases have a different bulk boundary correspondence, whatever that means. And we'll get to this later, okay? Sorry, what? No, this k is there's just complex conjugation. There's no, so it's times sigma 0 if you wish, yeah? If you want to write it like that. So it's just, yeah, just complex conjugation. Yes? No. There's no h to minus h in this case.
I don't understand, but what was the statement?
dz is equal to 0 here as well.
Yeah, but you can still add something proportional to the unit matrix.
Yes, okay, maybe I should have said that, but that doesn't matter for me, yeah? Because the unit, what Alex is saying, that we could add to the Hamiltonian, d0 of k times sigma 0. And of course, chiral symmetry would would not allow for such a term. The second symmetry combination would just impose again that this coefficient is even in K for time reversal symmetry, and yeah, for both. And this term here does not, so the spectral gap is not affected by this, at least the direct gap, if you wish, right, is d0 plus minus square root of d squared. And also, this coefficient here does not change the eigenstates, any property of the eigenstates. And so this sort of topological classification is unaffected by that thing. What is affected by it is the bulk boundary correspondence, and that's the distinction between these two cases. So what will come out is that these guys have boundary modes, these don't. Okay, when you add this order, yes, but without this order, it doesn't, right? It's a diagonal matrix. It's an identity matrix of in case. Yeah, no, I agree with this order, yes. But if I'm just talking about the, yeah. Yeah. Okay, the Bloch eigens, I mean the periodic part of the Bloch eigenstates is not changed. The plane wave part is going down the drain. Yeah, no, then I agree. Yeah, yeah. But so, okay, well, in what comes, we'll sort of generalize this for the Bloch eigenstates, not for the, yeah. Okay. Okay. So now we have this definition of some sort of characterization of topology here based on this this winding, but it's of course a little inconvenient because it's only defined for Hamiltonian that's a 2x2 matrix, and that might not be the level of generality that we are interested in. So let's try to find a formulation that does something similar but more general, right? Because systems usually have more bands. And so what we want to do is make a topological characterization based on the Wilson, on what's called the Wilson loop. Okay. So what we want to consider is, and here again we look at the concept of adiabatic evolution and so on. We want to consider the adiabatic evolution of a wave packet in momentum space, if you wish. So, and in particular, we are interested in the phase resulting from an adiabatic evolution, or the unitary transformation that results from adiabatic evolution. And so we want to go in momentum space from some initial momentum K in to some final momentum Kf, and we take a path. You see that I'm already going to a level of generality where I can go to higher dimensions. But let's, for the time being, we can still think about 1D. And that path is made of, contains a discretization, which we, let's say, call Ki. And we have n of these little points that are along the path. So in general, there's this path, there's the initial state, there's the final state, and then there's along this path many, and we'll let them go to infinity, obviously, K1, K2, all the way to Kf is equal to Kn. Maybe this is K2, K3, and so forth. Okay, so that's the setting. And now what characterizes our quantum system, the state of our quantum system at each point in the path is the projector on the occupied states. Right? That gives us all the information basically we need. And so that we call it P of Ki. And it's given by, so let's say we have a band, a system with n bands, and label these bands by A. Then it's given by this thing, UA of Ki. UA Ki. Okay. And notice that here I'm really not interested in energetics anymore. The only thing that interests me is where's the spectral gap. So these are n occupied bands. But in which order they are energetically and so forth, that is really not and should not be of interest because this is not a topological quantity. I can always fiddle with the Hamiltonian and change the order of the occupied bands. Yeah? So there's n bands here, and then let's say there's L bands up here. That makes a total of n plus L bands.
Sorry?
Mm-hmm.
You also assume that they don't cross.
They don't cross, yeah. Everywhere I have a gapped Hamiltonian along this path, yeah? Because I have, I mean, at least locally, right? Because I have this, that was the condition that there's a gap, right? And so we can write this as also with a unitary matrix, right? If I think about a matrix representation, I'll call this UKI, U dagger of Ki just for brevity. So this is, well, actually this here is an n plus L cross n matrix with the Bloch eigenstates. Okay, and now we can compute the amplitude of the propagation of this Wilson loop, or well, yeah. And this amplitude is now given by, depends of course on our path, by the limit n towards infinity of, and now I want to apply these operators in the order, in the sensible order, let's say, that on the right I start with the initial state and then and I go to the final state on the left. So we stop with some final state, and then there comes the product over all those discretized states. That projector, and then the initial state. Okay, this is the amplitude of propagation. That now depends on A and B. Yeah, this is a matrix because I have to say in which band do I start and which band do I end. Right. So this is a matrix. Okay, and let's first express this matrix in a slightly different form. Say again. This is a product? Maybe I should have said that this overbar means path ordering, so I can't choose an arbitrary order of these, but I should, start, as the path progresses, right? Put one after the other. But was that the question? No. Yeah, the gamma is the actual path, and that set of Ki's is a subset of points, and I'll let them go to infinity. So in the limit n to infinity, it should actually equal the path, if you wish. Yeah, right. Very good. You're paying attention to my notation. Very good. Okay, so what can I do? How can I represent this in a different way? You see that these are just creating, this product here creates overlaps, right, between these Bloch states. But interestingly, they are at different momenta, right? So usually, well, whatever usual is, but we might be more used to looking at overlaps at the same momentum between two Bloch states, in which case we can use orthogonality relations. But now, of course, there's no, a priori no relation of the Bloch states between the Bloch states at momenta k and another momentum. But of course, we can approximate this by a Taylor expansion and write UB as UB of k minus dk, let's say we write in 3D gradient UB of k plus order dk squared. Okay, stuff like that. And now we can use the orthogonality relation between these A and B. So it's delta AB minus dk times UA of k. UB of k. If you feel like you can exponentiate that, then you get minus dk u a of k k b of k. And that is sometimes, or actually most of the time, written as a gauge field AAB of k, which is also called the Berry connection. Berry connection. So now you see this Berry connection is, the definition of the Berry connection is exactly that, right? This overlap. And two remarks on this one. First of all, you see this again as a matrix valued. So there's A and B here. There's two different bands. Because in principle we have multiple bands. And the other remark is that you should be careful whether people are defining this as a real valued quantity or a complex valued. I didn't put an I here. Sometimes people put an I. So there's, don't get confused by that. Okay, so once we have it in this form, we can also rewrite our W here, and so we can rewrite it as either the limit n to infinity, and then this product 1 minus dk a of k. And that's now basically each time it's a matrix product, or again, since we exponentiated it, we can write this in the continuum limit as an integral dk a of k in the exponential, but then this exponential has again this bar over it because we have to make sure that we path order this integral, since A is now a matrix, so that's not, okay, that's not to be neglected. So this is a form of W of gamma. That's the Wilson loop operator. How much time do I have left? 15 minutes, very nice. So let's discuss a little bit the properties of this operator. The first thing that we should notice is that this guy depends on the choice of bases that I use, right? So this has these, in principle, is like this alpha, this AB indices. I can put them here. And they remind us that we've chosen a basis of our occupied bands at the initial and the final point. And of course, this basis choice is not unique. Yeah? in particular, in the point of view that I've taken, I can make a UN gauge transformation, so I can scramble these spaces up completely in the occupied subspace, and I still should describe the same physical properties as far as topology goes. Yeah? So this is gauge dependent. There is a UN. Okay, now that's a capital or a different U. So what? Let's quickly see what is gauge dependent and what is not in this game. So let's do this gauge transformation to our Bloch state matrix U of Ki, and I want to represent the gauge transformation by chi of Ki. Yeah, that's the UN. And then I get a new basis U tilde. Yeah? These are the U matrices that enter in our projector. And then what happens to the projector is that I get P tilde of Ki is U tilde dagger. U tilde. It's all at Ki, so I guess I can kind of maybe leave that go. And what you see magically, since this is at the same momentum, these chi and chi dagger go away, and this is the same as P. Yeah. So the projector on the occupied band, as you would hope, is gauge invariant. So is then the product of these projectors that entered the Wilson loop. So what would be the gauge transformation of the Wilson loop then? It can only come from the two end states, right? So W tilde of gamma must be chi of K final times W of gamma times chi of K initial. Yeah? These are chi dagger of K initial. Okay, so that's still not very satisfying. To get something that's more useful, we can consider a closed path where the initial and the final state are the same. And now in 1D, there is only one closed path, right? To come back to our Suschrieffer-Higa model, we would just go through the whole Brillouin zone, through the whole, that is a circle in 1D. Our path would just be the entire Brillouin zone. And if we do so, then of course, chi K final, because of the periodicity of the Bloch states, is equal to chi initial. And so then you see that W is still not gauge invariant, but it's gauge covariant, right? I mean, or it's, no, this is also gauge covariant, but you see that there's the same unitary transformation at the beginning and the end. So then the spectrum of W of gamma is gauge invariant. Right? It doesn't change when I conjugate a matrix by a unitary. And also maybe I should say that W of gamma is of course itself a unitary matrix on those, a unitary transformation on those n bands. And as such, it has a spectrum on the complex circle. Okay. Another important quantity or an important aspect of this spectrum is its trace. It's not, again, the whole spectrum is gauge invariant, so it contains physical information, but in particular, it's often interesting to look at the trace. And that's then often, or I define this now as what I call the Berry phase. So it's the trace of minus I log determinant W of k, or of gamma, sorry. And that Berry phase is, it can be anything. It's basically the angle, right, of this complex of the complex eigenvalues, and in general, it's defined modulo 2 pi. Yeah. If I had more time, I would explain that, when you go and make a large, what's called a large gauge transformation through this path, so a gauge transformation that itself has a winding number, you can change it by 2 pi, this Berry phase. Okay. And an alternative definition for it in terms of our gauge potential would be I times the integral along this path gamma of d k times trace of A of k. Okay. So now we've been doing all this stuff, and yes, please. Oh, so. No, sorry, I want to. Yeah, that's true. Sorry, shit. That, right? That's what I want. Here, but there I want to trace with the A. Yes, sorry. Yeah. Well, yes, that's very good. Did you hear? Okay. So now the thing is, back to our topology, we had the symmetry, right? The symmetry requirements, and we can ask now ourselves, do we get any information out about the topology from computing this phi? Yeah, and there we look back to the question of inversion symmetry. I'm going to be brief on this. Roughly speaking, inversion inverts the path, right? It inverts the order in which I multiply all these operators. And so any eigenvalue of the Wilson loop will just be complex conjugated by applying the inversion inversion operation. So that means when I have an eigenvalue e to the I theta, let's say, we'll go to e to the minus I theta under inversion. And now if my system is inversion symmetric, then I can say something about this Berry phase, which is the sum basically over all these eigenvalues. Phi b is basically the sum of all these eigenvalues. So it can only take two values in this case, right? Which two values would that be? 0 and pi, right? These are the only values that are that can result from a spectrum that has this property, yeah? That it's invariant under inversion. So so this gives us a topological characterization. For the second case, where we have the inversion symmetry and time reversal symmetry as the defining properties of our Hamiltonian. Okay. In the last 2 minutes, do I have 2 minutes? Good. Let me also give you the topological classification for the other case with the chiral symmetry. which doesn't go along these lines, but related ones. So for chiral symmetry, what I can always do is I can deform the Hamiltonian into the Bloch Hamiltonian, really, into one where I flatten its bands. What I mean by that is basically that I have a Hamiltonian which has some band structure, and it has occupied and empty bands. And now I'm basically defining a new Hamiltonian which projects all occupied bands to the eigenvalue +1, and all empty bands to the eigenvalue +1, and all occupied bands to the eigenvalue -1. And that's what I want to do. And such a Hamiltonian, you can show, always takes the form 0, Q of k dagger 0, if I am in the eigenbasis of the chiral symmetry. In the eigenbasis of S, where Q of k is a unitary matrix. And now comes just a piece of mathematics, namely that for these unitary matrices, you can define a winding number, nu, which is given by 1 over 2 pi ek, and now trace of Q of k dagger partial k Q of k. Okay, and this guy turns out to be always an integer. So we have now an integer classification of topology. And it turns out also that if you go through the math and you compute, for instance, for this Hamiltonian, the Barry connection, you will find that nu is equal to phi b over 2 pi modulo 2. So this is a finer classification here than the one that we have there from inversion symmetry. Inversion symmetry, we had only 2 options, C2. Yeah, we'll get some more intuition maybe later about, or like tomorrow, about what that means physically. Now with this chiral symmetry, we have more options, or a finer classification, an integer classification of topology via this winding number, but it agrees the parity of nu is equal to basically phi b over 2 pi. So there is a connection. And
Sorry?
Mm-hmm.
So maybe you were finding some time earlier, but by inversion symmetry you mean the time reversal symmetry, is that correct? No.
This means inversion symmetry.
Really, like a spatial
Yeah.
inversion?
Yes, spatial inversion symmetry.
So, okay, surprising. Okay, good. But it doesn't even map the, if you go in dimensional space, it doesn't even map the starting point to itself. So
It does. I mean, okay, let's say I should start at an inversion symmetric point, let's say at pi or 0.
okay.
And then that stays.
Assume that, okay.
Yeah, maybe I should set up with, yeah. So if you start at an inversion symmetric point, well,
Yeah.
I guess the spectrum, it doesn't even matter for the spectrum.
Okay.
But maybe it's easier.
Observable for
But it's really the reverse. I mean, all these, the integral gets really reversed. That's essentially the thing. The path gets reversed of your integration in the Wilson loop. That's what gives you. So suppose you start from an inversion symmetric point. The states on the side, they are what they are. But everything in between them is just, the order is reversed. That gives you the minus sign in the eigenvalues. That's so. Okay, maybe I used the time reversal symmetry to justify the form of the Hamiltonian. For this inversion, I think is enough. I don't see where I need time reversal now.
So it's not a more general
I think, yeah, I don't see where you need time reversal symmetry, yeah. Mm-hmm.
The relation between mu and phi is backwards here, right?
Okay, let's say mu modulo. Okay, you want this?
So mu 1, 2 times pi.
Yeah. Like this? Better, right? Mm-hmm. Good. Very good. Someone paying attention.
Pi by pi, right? No, it's 2 pi, it will become 0, and the right side is
Even more attention paid. No, that's true. So this thing is integer, and then, yeah, right, exactly. So very good. Very good. Is there anything else I want to say? Maybe not for today. Of course, we haven't talked about bulk boundary correspondence yet. So far, we haven't really said what this topological classification physically means. And that's for tomorrow. OK, thanks.